to the participants. Yeah.
Okay. So these are some few notations I use. As I said, it's going to be very elementary, and then just to have a feel on the few things. Okay. So let's look at a couple of fundamental results. There are many more. So let me start with the first one. The bounded entire function is necessarily a constant. Everybody knows that this is the statement of Liouville's theorem. Okay. This is a very simple statement which inspired a lot of people in developing several other aspects of the Liouville's theorem in different contexts, including in the context of quasi-regular mappings and Teichmüller's theory point of view as well, and so on. Okay, so therefore it's slightly more general theorem than the Liouville's theorem, which is again the proof follows from quasi-integral formula, is that entire function f whose growth is controlled by the power of mod z in some way with the power alpha. Alpha is a non-negative, complex, non-negative real number. So in that case, if this is true for even for sufficiently large value of r, that means outside a circle of radius r, then the function must be instead of constant, it reduces to polynomial of some degree. Okay. Then there is another consequence which comes from the naturally from the Liouville's theorem, is that if entire function which is doubly periodic, then it has to be necessarily a constant. This is also a known simple result. But apart from that, the simple example of entire functions like sine z, when you look at, so you will have sine z equal to w. If you put given any w, whether w is a 0 or non-zero, you can find infinitely many z for which sine z equal to w has a solution. Okay, which means the sine function takes a whole complex plane into whole complex plane. And similarly, polynomial, if you take identity function z, it takes whole complex plane onto whole complex plane. If we take z squared, it takes upper half plane onto the whole complex plane, lower half plane onto whole complex plane. Again, so therefore range of polynomial of degree is again whole complex plane. So more generally, polynomial takes the whole complex plane onto the whole complex plane. So when you look at e power z, it takes the whole complex plane into whole complex plane minus a single point. That's an exceptional point. Okay, but see, look at that. Sine is e power z is not an one-to-one function, but it's periodic functions definitely. Okay, anyhow, so therefore there is a general question comes from the Liouville's theorem, is that suppose if you take the condition of the Liouville's theorem statement, f is an entire function, instead of bounded, if it takes value outside a disk of some positive radius, then you see that 1 over f is actually entire function and hence bounded by some number and hence reduces to constant. So this clearly indicates there is something interesting to going around the whole class of entire function. That's what extracted by the next statement. The range of a non-constant entire function is a dense subset of C. In fact, if we go a little bit beyond, and if entire function omits two values, the functions that we know, for example, polynomial never omits any value, sine z never omits any value, cosine never omits any complex number, but e power z omits only one value, 0. So that gives a clue. Is there an entire function which can omit more than one point? The answer is given by this statement. If an entire function omits two values, then it must be none other than a constant function. In fact, much more than is true. That was given by this, Picard's great theorem. If a function is as an essential singularity at a point, that means it is, for example, it is analytic in a deleted neighborhood. And when you expand it as a Lorentz series about that point, it will have infinitely many powers of z minus a, negative powers. Okay, so in that kind of functions, the range, the complement of the range of the deleted neighborhood is a singleton set. So this is a Picard's great theorem, very, very nice theorem. But of course, this theorem, the Liouville's theorem, if you replace analyticity by continuity, of course, it's not true, because you can have many functions that are continuous, bounded in C, but it could, there are non-constant. I mean, non-constant, bounded, continuous function at C are there. There are many. Okay. So therefore, entire is an essential condition in that theorem. Anyhow, this is one of the fundamental theorem, at least to me, to the student's point of view and the young researcher's point of view. Liouville's theorem creates a lot more thing. And one of the proofs about Picard's great theorem comes from what's called the Landau's theorem. Okay, if you have a non-constant analytic function, the range contains a disk of radius, some positive radius, and the radius is universal constant. So there is a universal constant such that a non-constant holomorphic function in some disk always contain a disk of some radius, and that radius is some universal constant. Okay, anyhow, in the disk, of course. Then the question is, what will happen if we replace entire by meromorphic function in the case of Picard's theorem? So which means, suppose there is a meromorphic function which omits 2 points. Can we conclude that it's a constant? It's not. So therefore, here there is an example first. Start with an example. This phi by 1 over exponential of z plus 1. It has infinitely many zeros for the denominator, and hence it has a pole, and the only singularities of this quotient are simple poles, you can see, and you can also check that they omit 0 and 1. These are the 2 points. So there are meromorphic function in the complex plane which omits 2 values. So there exists non-constant meromorphic function which omits 2 values, 2 distinct values. Okay, so this example shows that the meromorphic functions in C can omit, of course, 2 complex values. So then the question comes, can it omit 3 values? Well, it is not. So that's what the next theorem says. Every meromorphic function which omits 3 distinct values must necessarily a constant. So this is the bit of development about this Liouville's theorem, Picard's little theorem, then Picard's little theorem from meromorphic function, etc. Okay, so this is just have a flavor about some kind of introduction to this topic. Okay, now we come to the very, very important theorem in complex analysis. There are 2 nice theorems in complex analysis. Riemann-Meeping theorem is an existence theorem. And then there is a Weierstrass product representation, or if you have an entire function which has infinitely many zeros, you can explicitly determine the function f in terms of the zeros of the given entire function. That's more explicit. So here this theorem is just existence. Suppose you are given 2 simply connected domains which are not the whole complex plane. So are there a conformal map between them? The answer is yes, but it gives you existence. And in the sense that randomly, if you are given 2 simply connected domains which are not whole complex plane, can you determine explicitly? It may be difficult. So therefore, the computational complex analysis play a role. But this existence theorem helps to extract a lot more interesting results, applications in many contexts. Okay, so this theorem says the following. Okay, let's start with a simply connected domain. That's not the whole complex plane. Question is it conformally equivalent to the disk? If we prove yes, then you can say that two simply connected domains are conformally equivalent. From this you can derive. Okay. Of course, when I say simple economic domain, here the domain which are not the whole complex plane. Okay. Well, the uniqueness is determined by this value. Because we are looking at a simple economic domain, and we want to find a unique conformal map from omega onto the unit disk, which means existence of an analytic function which is 1 onto mapping of simply connected domain onto the unit disk, for which one point ticks to 0, whose derivative is either positive or fixed argument. That's fine. Okay. This angle preserving mapping in some way, or some ways we call conformal mapping theorem, whatever it is. Okay. Well, the nice class of examples come from the Mobius transformation, which is one of the phenomenal result. Nice class of mappings in the case of Riemann mapping theorem. Okay, good. So this theorem is very well known, and everyone should at least know its statement and its key ingredient made in the statement, and how it's useful in developing several important concepts in the classical complex analysis, and which led to theory of coarse-conformal map, and hence determine its connection with the elliptic PDE, and hence its connection with the higher dimensional, and so on. So this is very, very powerful theorem in complex analysis. Okay, so now let's go back to some very, very elementary aspects of determining or understanding Riemann mapping theorem. Riemann mapping theorem describes about the univalency of the function. Okay, so therefore we must know, we are talking about Riemann mapping theorem on a simple economic domain. So of course the inverse is again holomorphic, and hence the inverse is also 1 onto. Therefore, without loss of generality, often we look at Riemann map defined on the unit disk. It is convenient in some way because you have the power series representation about origin, and hence you play around developing ideas from power series methods. So a natural question is, what are the necessary and sufficient condition for a function to be 1, 1? So this question has many different answers in different settings. One way is looking at some kind of a nice functional inequality which shows the function is univalent. Other aspects is, if you have a power series about origin, if the function is analytic in the disk, for example, then the necessary condition or sufficient condition should come in terms of the Taylor coefficients. So there are two aspects. One is in terms of functional inequality, that led to different information, led to many geometric objects are coming from there. And other aspects is determining necessary sufficient conditions in terms of coefficients for a function to be 1, 1. So when you deal with power series. Okay, so let's look at this first very simple theorem, Wolff-Nozero-Warshawski theorem. If you have before we get into the statement of this theorem, in the case of functions of one variable, real functions of real variable, so we know that the derivative positive, that means if a function is monotone, then it's 1, 1. If the function is increasing or decreasing, of course it's 1, 1 on that interval wherever it's monotone. So a natural question is, what's the complex analog of that statement? But in the complex analog, when you look at the derivative f prime z, it's a complex number. We cannot talk about this number is bigger than 0 or less than 0, but we can talk about this function takes value off plane. Instead of bigger than 0, you take real part is positive or real part is negative. Then we can talk about whether such things, the analog of the previous statement, what I said, f prime positive implies f is 1, 1 in the real case. Similar thing does hold or not. That means real part of the derivative is positive. Does it imply f is 1, 1? The answer is yes. So the first clue comes from the classical real analysis to get into a nice analog of that one. That's what this theorem says. So if the derivative is positive, I have allowed rotation factor. It doesn't matter because derivative is positive. When you allow a rotation, then it's still an off plane. So it's not right off plane, it's an off plane. It's fine. Okay, if this is true, then f is 1, 1. And this theorem is very, very easy, but it gives you very nice geometry that we are going to look at next. Okay, so the proof is very trivial, and I want you to know this theorem. Okay, the domain is a convex domain. For example, disk is a convex domain. Unit disk, for example, or ellipse off plane. So it's all convex domain. So that means any 2 points can be connected so that the line segment stays inside the domain. Okay, when D is convex, the line segment connecting these 2 points, Z1 and Z2 are arbitrary points. Look at the line segment connecting them. So that means you parameterize the line segment by the parametric form Z of T. Okay, this is a parameterized curve. That means they're parameterizing the line segment connecting the 2 points Z1 and Z2. Okay, now look at the left hand side. The difference between these two values, f at Z1 and f at Z2, look at the difference. You write this as an integral Z1 to Z2 f prime. This is again the classical theorem. The value of because f prime is a analytic function. F is analytic, so therefore all derivatives exist, and hence f prime is analytic. There is a theorem in complex analysis. The value of the integral, as long as the integrand is an analytic function, is an independent of the path which connects these 2 points. And hence, you could look at, this is a fundamental theorem of calculus in complex form. So therefore, the difference between the n values are simply this one that comes from fundamental theorem. Now I use the parameterized form. Then when they take the derivative of z, you get z2 minus z1 as a factor that comes out. And then the integration is with respect to t. This is your Riemann integral, where the integrand is f prime evaluated at an arbitrary point on the line segment connecting z1 and z2. So it's a complex number. That means you can have a real part and imaginary part, and the real part as positive, in the integrand, and forget about the imaginary part. So therefore, 0 to 1, real part of this integrand, as a Riemann integral, this produces a non-zero complex number, first of all. Okay, it produces a non-zero complex number. So therefore, when 2 distinct complex numbers Z1 and Z2 are chosen, and this f of Z1 minus f of Z2 must produce a non-zero complex number, and hence they are distinct from 0, and that gives you 1, 1 immediately. So that's it. More precisely, I have written down separately. Look at Z1, Z2 by Z1 left hand side, and then look at the modulus value. Modulus of a complex number is bigger than the real part of the complex number. Now it's a Riemann integral. Integral is over the real interval 0 to 1. So I take the real part inside, and this real part, the integrand, is positive, and that means there are u plus iv, where u is non-negative, and hence the corresponding Riemann integral should produce a non-zero complex number, and hence this difference will be this will be always a positive real number because of the assumption. Okay, so this gives you very, very simple proof. Okay, now I have made the statement that analytic function in a convex domain. I made this as an equivalent statement. Okay, now I look at an equivalent formulation of that. So now I start with a function analytic in the disk. So let me start with a conformal mapping of unit disk onto a convex domain. Such map exists because of the Riemann mapping theorem, because convex domain and the unit disk, and their two simple equivalent domain, there is a conformal map. Okay, good. So such a map, I call it G. Now I rewrite the statement in a way you involve this G in the assumption. So that's what your statement comes here. Of course, this alpha equals 0, it doesn't matter. I mean, you can choose alpha equals 0. It doesn't matter. This is a more general when you put alpha, some real number, and then, rotate it by this angle alpha with this quotient f prime over g prime. So the equivalent statement is given here. So the proof is very easy. From the proof, you'll know how you get this one. So the range of the G is the convex domain D. So G inverse exists. So you can look at F composed with G inverse is a well-defined function. And this is defined on the convex domain D. And then as per the previous statement, if you convert this into the previous statement, you will see this nice identity. And that means H prime of points in the convex domain is simply the quotient. So for example, if this quotient has a real part positive, that means the real part of H prime is positive, and hence H is univalent. But H is univalent, G is univalent, composition of two univalent functions is univalent, and hence F must be univalent. And that's the proof of this theorem. So what is interesting here? So the univalent is just a nice thing, no doubt. But can we say something more about the image domain? In fact, it is well-known result that I don't want to get into that theorem. If this condition is satisfied for some value of alpha, it could be 0, for example. For some G, this G could be even identity function. Then it becomes a real part of the derivative, simply. Then the range of F is a domain which is called a closed convex domain. What does it mean by closed convex domain? It means the complement of the domain is connected by a non-intersecting half lines. That means the boundary will not have a hairpin turn. So you have a boundary without a hairpin turn. That means you can, if it does not have a hairpin turn, you can connect the complement by a non-intersecting half lines. So the function satisfying this condition means the range will be always a closed convex. Made a nice result, but it's a geometry. Okay, so let's not get into that more. So this is important to know. So similarly, if this happens, the range of F, again, a closed convex domain. That means the complement of the domain is connected by non-intersecting half lines. Okay, very nice geometry. Okay, so next question, as I said, I want to create more example. Given F prime by G prime, and then I need to compute this quotient, and I want to know the real part is positive. Sometimes it may be difficult to compute that. So therefore, we want to extract some nice simple condition in order to extract nice class of examples. Okay, the answer is yes. Look at this one. A function which has a power series representation. Conveniently, I normalize the power series. When this condition is satisfied, that means n times modulus an is summable, whose sum is bounded by 1. Then F is 1, 1. Okay, so when I derive this condition, okay, so I use the previous thing. It is very simple. Look at the derivative of the given function. Subtract the 1. Look at its absolute value. You get this, power series whose coefficients are n times an. I started with the, function in the unit disk. So when mod z is less than 1, use that, triangle inequality. So mod z less than 1, it gives you n times modulus an. When this condition happens, then f prime minus 1 in absolute value is less than 1. That means f prime lies in a circle centered at 1 with radius 1. That means it lies, the f prime, the derivative lies in the half plane. That means subset of the half plane, because the unit disk, the disk centered 1 and radius 1 lies on the half plane. So and hence f prime has a real part positive automatically, and hence univalent. So when I said this thing, then naturally Of course, we can get a very nice class of ANs. You can get AN in a very, very small, like 1 over n power, say 100 you take. AN is 1 over n power 100. Then you can see that summation n power 100 minus 1, always bounded by 1. For large number, you can always see that such things can easily get. So therefore, you can get nice class example. But then you will see that you can again show something more than that. In this case, not only F is univalent, the conclusion of the previous theorem says that the range will be a closed convex domain, but I could even say that the range will be a star-like domain. What it means is, you can, sitting at the origin, you can see every guys on the boundary. So that's what a star-like domain. Sitting at the center, that means sitting at the origin, you can see everybody who is sitting on the boundary. That means the line segment connecting 0 at the boundary of the range is, the line segment connecting 0 with the boundary will be always lying inside. Then the domain is called star-like. Okay, so you can draw the picture of a star-like star. You keep at the center, so you can see everybody at the boundary. Okay, so such things also follows from the next consequence of this one. Let's not derive that. Okay, it's getting late, so I have to get into the topic. Okay, the most fundamental and the central object in the theory of univalent function, which is one of the advanced course people deal with at least this statement of what is called the Bibaba conjecture, which was proposed in 1916. If a function is, of course, normalized in a convenient form, because we have a power series about origin, that's analytic, and we start with the univalent in the unit disk. Univalency is not going to be disturbed by subtracting a constant, so ignore the first constant a naught, and then every univalent function must have its derivative non-vanishing, and hence a1 must be non-zero. So I divide by a1, then it is normalized. This is just a convenient. Okay. So when you look at a normalized univalent function that's analytic, Bibaba conjectured that if a function is univalent, normalized by this, the general coefficient is bounded by n, and then equality holds if and only if f is a Kobe function or its rotation. That's mean. This is one of the powerful theorem in 1916, which took almost 70 years to get a proof. During the 70 years, the complex analysis developed from Riemann mapping theorem reached a stage where it's tool to use everywhere. Okay, but anyhow, so the problem was solved finally by D. Branches in 1985. D. Branches himself is not actually a complex analysis man in a real sense. He works from summability theory, and he managed to look at a proof via two different ways. One is looking at Lohner's differential equations coupled with special functions, special function more precisely hypergeometric series, fascinating subjects for Ramanujan. In fact, he uses some work of Ramanujan in some way that was developed by Richard Aske later. Okay, so therefore this problem is solved. Okay, now it is solved. Then natural question is, why do we use only the analyticity? Okay, why do we use analyticity? Every analytic function, if you look at the analytic function, the real and imaginary parts are harmonic, and they satisfy Cauchy-Riemann equation. So you will naturally look at, okay, suppose it doesn't satisfy Cauchy-Riemann equation, but they satisfy Laplace equation. Then they are called, complex valued function that's harmonic. So they do not necessarily satisfy Cauchy-Riemann equation, but they satisfy Laplace equation. For example, f of z equal to z bar square. So it is not a harmonic. It's not analytic, but it's harmonic. Similarly, z bar plus z bar z square. That means conjugate of z plus z square. This is not analytic, but it's harmonic. So suppose if you insist harmonicity together with univalency, whether a natural analog of this statement holds, whether things that are being developed in the case of conformal maps could be developed for harmonic mappings or not. This is a natural question which actually seriously began almost in the same period after the proof of de Branche's theorem in 1985. So my second part of the talk is more close to that. Okay, let's a little bit browse through this thing. Okay, let's look at the picture of Bieberbach, who lived until 1982, and de Branches from Purdue University. There is a actually, I think the mathematical community celebrated this theorem, and they released a stamp in US with modulus an less than or equal n in US. Okay, so this statement also appeared in a stamp in US, and that was celebrated when there was a celebration about the proof of de Branche's proof for the Bieberbach conjecture. Okay, so this celebration occurred with the stamp release also. Anyhow, so that's about this development about this. So since this was not proved, people try to look at a constant, at least to prove with some constant. And then for A3s, there are some new techniques were developed. It's not the proof of A3 is less than or equal to 3 important. It is a technique that comes out new. That's very important. And that's what people develop several tools. And de Branches did not prove this Bieberbach conjecture directly. There were several sequence of conjecture which implies the Bieberbach conjecture. And de Branches proved such a conjecture that's called, Millin's conjecture. Millin conjecture implies Bieberbach conjecture. So he proved Millin conjecture, and hence he proved Bieberbach conjecture. Because of that, several other conjectures become true. Okay, good. So that's about one of the topics that led to this. Let's quickly browse through, at least for A2 less than or equal to 2 case. So let's look at its connection with the meromorphic function. So if f is univalent, it cannot have more than 1 0. Okay, so therefore 1 by f, if you remove the 0, then 1 by f becomes a meromorphic function. Okay, so that way, so you can connect analytic function with meromorphic function. If it's the unit disk, then 1 over f and then z replaced by 1 by z, then you go from inside of a disk onto outside of disk. Okay, let's look at the typical element that are univalent and meromorphic outside the unit disk, and you look at the power series expansion of such a thing. What is interesting is there is a proof which comes from Green's theorem, what's called the area theorem, to describe single line integral in terms of double integral, and then convert that tools into functions of complex variable. Then you get a proof of this theorem. Let's not get into the proof. So if you have a univalent function which is univalent outside the unit disk, that means meromorphic with the simple pole at point at infinity with residue 1. That's what z appears here. So when you convert this into z by 1 by z, then you have a g of 1 by z. That's meromorphic with simple pole at z equals 0. So now we convert from inside to outside. So therefore, this is a meromorphic function with simple pole at point at infinity with residue 1, in fact. Okay, then there is a nice theorem which gives you bound for the coefficients in this way as a necessary condition. So in particular, you will see that this modulus of B1 has to be less than or equal to 1 because the summation is bounded by 1, and hence n equal to 1. This first leading term must be bounded by 1, and that's exactly B1 less than or equal to 1. And here the equality holds if and only for functions of this form. It might look like a simple observation, and this observation helps to make the Kobe function is a real extremal function, but for the coefficients problem proposed by Bieberbach. Okay, let's Okay, so we can get the proof of that. Let me just outline the proof quickly in a couple of lines. So look at the function that's univalent in the unit disk. I want to prove this Bibaba conjecture for n equal to 2. What we do is look at the square root of this one. You can easily prove that the square root of this one is all f is analytic, univalent. Then the square root transform of f is also univalent and analytic in this sense. That means dividing by z squared by z squared in a way to get a power series in a compact form. And when you look at this first coefficient is this. Now I look at the inversion of that, but changing from disk to outside the disk. So I replace mod z less than 1 by z. That becomes in 1 by z. Then it becomes bigger than 1 in absolute value. So phi is defined outside the unit disk, where the leading first coefficient is minus a2 by 2. By the previous theorem, that has to be bounded by 1, because G is univalent if and only if phi is univalent. G is univalent in the unit disk. So therefore, the initial coefficient is bounded by 1, and hence a2 bounded by 2. And going back to from the previous theorem, you can get this thing. Okay. So now I'm going to extract few nice observations. Okay. Look at the first theorem. I want to insist the coefficients are integer. That means I am looking at univalent function that has a power series representation, where the Taylor coefficients assumes only integer values. Then what can you say about such class of function? And this problem was proposed in a conference somewhere in 1940s by Heyman, and they came out with a proof. There are none other than 9 functions. Okay, these 9 functions are somehow nicely behaved extremal function in different subclasses of univalent function whose range is some sense convex domain or closed convex domain or domain with 2 slits, and these functions play the role of extremal. Okay, the proof is again easy. Okay, as I said, you begin with the power series representation of f, assume that ans are integer, look at 1 over f and rewrite in terms of power series. It is whole in the punctured disk. Remember, f cannot have more than 1 zeros because f is univalent. Therefore, the only 0 here is at the origin. So therefore, it is the f is non-vanishing in the punctured disk, and hence as a power series representation, call this power series in this form. Now cross multiply by f on both sides, you get an identity. Look at now compare the coefficients of z powers on both sides. Then you will see immediately when an is integer, all the bn must be integer. And remember, this is also univalent, and hence by the previous theorem, summation n times modulus bn also bounded by 1. So therefore, n times modulus bn summation bounded by n 1. So if bn is integer, the integer cannot be more than 1 in absolute value. So therefore, this will lead only to class of functions for which b naught is not 0. B naught assumes value either 0 and 1. B1 assumes either value 0, 1 and minus. These are the 2 possibilities. And that led completely these 9 functions. Okay. So that's a proof of this. Very nice, simple consequence. Remember, I have proved one nice theorem and then one nice theorem about Friedman. Of course, Friedman proof is lengthy. There are several other proofs. This is the simplest proof I come across, and I simplified a little later, and that simplification leads to this half-a-page proof of this. Okay, this is not 3. It should be omit this 3 here. It's by typo. Okay, Now I go to the second half of my lecture. I need to develop some preliminaries and raise questions. How these conformal mapping questions, at least the few questions that we discuss as of now, and let's raise these questions in the context of harmonic mapping, and then see how this helps to develop something further. So that's my interest here in this talk. So as of now, whatever we do, they're all basic complex analysis. We talk about Riemann mapping theorem. We talk about a condition which ensures function is univalent in terms of functionals. We use only one functional, that means real part of f prime positive. And then we use only one condition, sufficient condition, summation n times modulus a n bounded by 1. One necessary condition, that's exactly the Bieber conjecture. There are many more such results, which I don't say here due to the time limit. Okay, then I ask a question about what will happen to those class of univalent function where the Taylor coefficients are just integer. This contains only 9 functions. So therefore, natural to think about these questions in a broader sense. That means by dropping analyticity by a harmonicity, for example. So we look at instead of subset, we look at a larger class of function and ask these questions, whether these questions are meaningful. Conformal mappings have a lot of tools. Already a lot of tools are there. But the harmonic mappings do not have that much tools to utilize. For example, inverse of univalent harmonic functions need not even be harmonic. So therefore, things do not work very well. Okay, good. Anyhow, so let's start with just a mild definition of harmonic. Real harmonic, everybody knows. Okay, so omega is suppose we start with a simply connected domain. Of course, need not be simply connected domain. You could take multiply connected domain also, a ring domain also. So our concern is simply connected domain. It's harmonic. It satisfies Laplace equation. Okay, then when I say complex valued function, that's harmonic if u and v are harmonic, where u and v do not necessarily satisfy Cauchy-Riemann equation. That's all. That's all. In terms of complex form, this f sub z bar equal to 0 is the equivalent formulation of the Laplacian. Okay, so del f equal to 0 is if and only if the partial derivative of f with respect to z and z bar variable equals 0 on the domain. Okay, so now we know the definition of harmonic function on the complex plane. Now we want to connect such complex value harmonic function in terms of analytic function. That's a simple exercise coming from basic complex analysis, and that we will come back. Okay, so now my question are the following 4 questions. Okay, so whether this theorem about univalency, the Wolff-Noshiro-Warshawski theorem, is its harmonic analog. What is the harmonic analog of that one? Okay, next thing is, what is the harmonic analog of Bieber conjecture? And when I ask for a harmonic analog Bieber conjecture, it's not just an abstract setting. When the question is raised, you will see how the geometry is playing a big role, how the differential geometry and minimal surfaces got interesting in this setting. So that's what the planar harmonic mapping plays a very great role, not by asking questions in the formulation of classical setting. Classical setting is one, but the second part is its connection with various other fields like minimal surfaces, more generally differential geometry, where there is a notion of Schwarzian, pre-Schwarzian derivatives, and hence there is a settings in the tight-Miller spaces, and hence it goes to all the way to string theory and all that. So it is not just raising question in the classical form. Okay, then the question is harmonic analog of Friedman. when I ask for harmonic of Friedman, see, Friedman question is connected with the power series representation of the function involved. So therefore, an is there. So therefore, when you look at harmonic analog, so if you look at a harmonic function in the unit disk, our natural question is, how do you connect every harmonic function in terms of some sort of a power series representation which will involve some coefficients. Only then we can propose how the an or integer is transformed there also. Okay. Then the last important question is harmonic analog of the subsequent theory that are being developed in the conformal case. It is not just these few questions. There are a lot more interesting questions in several ways. Okay, for example, we look at the Bloch's theorem. Then there is a Bloch's theorem that led to development for the Picard's little theorem proof also. And then there is a related conjecture about Bloch constant that remains open. So therefore, when we look at the analog of that one in the harmonic case, it's more complicated. It's not that single formulation of analog. It's various formulation of analog of that particular settings. Okay. Okay, so let's first question is the following. So when you have an analytic function, and then we look at the Jacobian, and the Jacobian is absolute value of the derivative square. Okay, now when that is non-zero, then it's locally 1, 1. But that is not true from functions of several variable Rn into Rn. Fortunately, this result is true. The non-vanishing of the Jacobian is necessary and sufficient for local univalency is true in the case of planar harmonic mapping. This is done by Levy's theorem. So that's one of the fundamental theorem, which means if you look at a complex value harmonic function that is locally 1, 1, then the derivative is non-vanishing. Of course, when the derivative is non-vanishing, there is an inverse mapping theorem in the Rn, and that also holds for R2, and hence non-vanishing of the Jacobian means it's inject to locally. That's clear. But the other way is not that trivial, and that was proved by Levy in 1936. Okay, the first key has come in now. Okay, now second important exercise, F is a complex value function, U and V are harmonic in C. Now I am looking at the unit disk. U and V are harmonic in the unit disk. So U is harmonic, so therefore you can extract an analytic function whose real part is U. Similarly, V is harmonic, so I can find the analytic function whose real part is V. So that comes from a basic complex. Now you sum it up, U in terms of the first analytic function, V in terms of the second analytic function, and then simplify, then you will get every harmonic function can be decomposed into sum of analytic function and conjugate of analytic function in the unit disk. Of course, this is true for any simply connected domain. So I'm looking at only for this case because I can write them in terms of power series about origin for both for G and for H. So that's what the interesting. So now I can ask the question. So I need to change F prime derivative positive in terms of derivatives of H and G prime. That means in terms of partial derivative with respect to Z and Z bar of F. Okay. So when you look at F sub Z, that is exactly H prime. When you look at F sub Z bar, that's exactly G prime conjugate. So therefore, I can write the Jacobian in terms of H prime and G prime. That's what the first setting I do. So the Jacobian is written in terms of H prime, G prime, and look at the first term, modulus of H prime square, modulus of G prime square. When I say this is positive, it is sense preserving. and hence locally 1, 1. Okay, so once it is positive, then H prime cannot be 0. So therefore, this quotient is well defined. So therefore, non-vanishing of the Jacobian provides 1 to 1, but positivity of the Jacobian provides a sense-preserving map. So every sense-preserving map induces the quotient, which we call second complex dilatation. That's G prime by G H prime. Remember, because this is Jacobian is positive, this is bounded by 1. So every sense-preserving harmonic mapping induces a dilatation, that is, induces an analytic function which is bounded by 1. This is exactly the hypothesis of, the Schwarzschild lemma, which is one of the another powerful simple result led to the development of Poincare metric and things like that. Okay, so one natural question here: if f is entire function, which is 1, 1, then it is none other than the linear map. So a natural question is, what is the harmonic function which is univalent in the whole complex plane? You can prove that this is exactly none other than affine map. Again, the proof comes naturally from the Liouville's theorem. So that's why I say Liouville's theorem is powerful in developing many simple results which led to development of several other new. So in other words, there exists a no harmonic univalent mapping of the whole complex plane onto a proper subdomain of the complex plane, similar to the statement of Liouville's theorem in this form. There exists no analytic, that means entire map of disk onto a proper subdomain of C. Okay, right. So this is an easy statement, but one should remember this proof comes from Liouville's theorem, and also comes from assuming this sense preserving without loss of generality, and hence there is a dilatation. All that is used in the proof. Very simple anyhow. Okay, so next let's look at some simple example. Look at a nice example where the analytic part is Z, co-analytic part. When I say co-analytic part, that is the part which appears with a conjugate. That means H plus Z bar. So F is H plus Z bar. H is called analytic part. H is called analytic part here. And G is called co-analytic part. We call co-analytic because it is a conjugate of analytic function. Okay. So now the co-analytic part is Z squared by 2. And it is easy to check directly that this is univalent in the unit disk. Okay. And more generally, you could also see that Z power n, Z bar power n by n is univalent. You can easily do this simple exercise. Anyhow, okay, now you see the picture of this. There are 3 cusp points. Okay, when Z squared is here. When if you have Z cube, you will see there are 4 cusp points. When you see Z power 4, you will see 5. Z power n by n, you will see actually n plus 1 cusp points. You can actually prove it analytically. Okay, anyhow, so these are just the images of some points. Okay, now, okay, let's go look at harmonic analog of the first result that I mentioned. That's called Wolff-Nosyrov-Warshawski theorem. In the analytic case, this co-analytic part does not appear. That means G bar vanishes, and hence G prime vanishes, and this leads to that theorem. Okay, so you can ask, what is the proof? Again, the proof of fundamental calculus. You look at the convex domain D, take 2 distinct points, look at the difference between them. Then you write the derivative. Instead of the derivative, you write d by dz of f of z of t. The z of t is the in a parametric representation of the line segment connecting these 2 points. Now you have to have the partial, because f is a functions of z and z bar variable. It is not independent of z bar. It also depends on z bar. So therefore you have to split fz bar, and then you get quickly the proof. So for the moment, I don't make the statement of the proof proof follows exactly on the same line, just to 2 lines. So therefore, one of you could work it out, and all of you can work it out as a simple exercise. Okay. Well, the same thing here. You have F harmonic, and hence there is a decomposition, and hence there is H and G. They are analytic, and analytic in the neighborhood of origin, for example, to start with. But this sufficient condition, this condition ensures that both H and G are actually analytic in the unit disk. Okay, by root test for reducer convergence shows that when you begin with H and G analytic in the neighborhood of origin, this condition ensures that actually it's analytic in the disk at least. Okay. Then Jacobian is positive, that led to this one. Okay. And then again, same way you can prove this theorem. I leave it again for the moment as a simple exercise. So anyhow, these 2 theorems are analog. Of course, this proof you can also find from my paper with these 2 Japanese mathematicians. These 2 are very simple result. So it was part of a basic result in the introduction. Anyhow, so this lecture is not for people who know the theory, but people who want to get into this basic lectures on this part. Okay, so these 2 are elegant result. Again, you will ask, if satisfies this condition, does it mean the harmonic function takes disk onto a domain which is again close to convex, which means the complement of the range is connected by non-intersecting half lines? Answer is yes. It is also true. In fact, much more than is also true in this case, that the range is also a star-like domain. So here we have proved 2 results, that holds in the conformal case also holds in the harmonic case. So the harmonic analog of these 2 simple results goes easily to harmonic case. So let's look at the next question before I get to the second question. My second question was this one. What is the question? If we have a function, harmonic function, now there is a analytic part H, there is a co-analytic part G, therefore there is a Taylor coefficient for the analytic part, there is a Taylor coefficient for co-analytic part. That means AN and BNs are involved. If AN and BN are integers, then what can you say about the class of all those functions having integer coefficients? Here in the case of Feynman theorem, you have 9 functions. But in the case of harmonic mapping, this question was proposed in a conference in 2006 in Chennai, where there were about 40 foreign participants. This conference was a conference plus a workshop for harmonic mappings. It was a serious workshop. That was a time I started learning the subject. I learned from the speakers of that conference. And from there, my working style on harmonic mapping started. That's from 2006 onwards. Then I started reading that basic contents, and I first wrote my survey article on that subject to understand the basic tools that holds in the conformal case but not in the harmonic case. And during this process, this question was raised, and we discussed this for many people. We couldn't get answer. Then later, some years ago, myself with my Chinese visitor worked on this problem again. We found an answer to this question, and we found a more general answer. And the first typical answer is, if you look at the harmonic mappings having integer coefficients for the analytic and co-analytic part power series, there exists no non-conformal map. There exists no non-conformal map having integer coefficient. It's surprising result, but that means if you look at the harmonic mapping where an and bn are integers, then they are forced to be just only these 9 functions. So that's very amazing, simple result. But then we proved something more after that. So therefore, one nice thing is that the analog of this theorem, if you ask, there are only 9 functions in the case of univalent harmonic mapping having integer coefficients. These are all conformal maps. Remember that. They are all conformal maps. They are univalent mapping of discontinuous domain, which is, either convex, star-like, or, closed convex. Okay. So, so that's so Friedman result as analog of that one has been solved. Now that question is done. Okay. Now I ask the second question. Not the second question. Probably this is a final question, which deals with harmonic Bibaba conjecture. Okay, so the question is first to determine the extremal function. That itself requires a nice, imagination, how to look at problem which is analog of Bibaba conjecture, where determining extremal function and then testing with that extremal function for certain special families. And this was a very nice introduction, nice results on this topic in a paper by Clooney and Seelsumal, 1984. Clooney made several conjectures during his career. He proposed several conjectures. He proposed several conjectures on harmonic polynomials. He solved several conjectures as well. And one of his conjectures was the length of ray images under conformal map. And his conjecture was solved by Hall later, Richard Hall, who is basically a number theorist, person from complex analysis, but not so closely, but more on number theory. And then he proposed a general conjecture about the length of ray images under a special conformal map. And that problem was open almost for 40 years. And that I recently solved, and the paper appeared. Paper has to appear, but it's in archive. That's called the Hall's conjecture, or the star-like mappings of order alpha. And it issues several lemmas. They are technically harder in some way, but could be verified, those who are interested on that. Okay, anyhow, so there are, so Clooney, Seelsumal is very, very, very good in forming nice proposal for the new beginning on many topics. And this is one such topic, harmonic univalent maps. After that, a lot has been done. Peter Thorne has written a nice book on univalent harmonic mappings. And then there is a book on harmonic mappings in Rn. So that's the development of this theory for the higher dimensional. And in the case of planar harmonic mapping, this is the first leading paper which deals with the harmonic analog of the Bibaba conjecture, and hence the theory of univalent functions in that particular part. Okay, so the conjecture is that you have a 2 power series involved for a harmonic function because of the decomposition of f into h and g bar. So these 2 power series have the an and bn coefficients. I have chosen here n runs from 2 to infinity. Of course, I can transfer this result into 1 to infinity. And this is for some reason 2 to infinity is nice, because the class of the class SH0, which I denote for sense preserving univalent harmonic mapping defined on the disk. And this class is both normal and compact. Whereas if you allow B1 coefficient, it is normal, but it's not compact. and hence the compactness requires to set this conjecture. But from this you can actually get forth, you can get conjecture for general an and bn, even if you allow n equal to 1 to infinity, by making the correspondence between f in sh naught with the class without b1 being 0. So you can connect that with an affine map. So that affine map gives you one-to-one correspondence between the class sh naught with the class sh, which means allowing b1 not equal to 0. So with that you can do. Anyhow, what is that? Then an is bounded by this number, and bn is bounded by some capital Bn, this number. Okay. And then when you also look at the difference, absolute value difference of these two coefficients, they are bounded by the absolute value of the difference of these two. In fact, you can remove this absolute value here, but I put it just for making the statement analog. Okay. And this difference with respect to capital An's and capital Bn's, exactly n, when Bn's are 0, that means you are going back to the Bivouac conjecture. And that's why this conjecture was made in this form. Okay, so therefore an extremal function, that's something like similar to Kobe function. So making the Kobe function available for this family is a typical task. And that
Ponnusamy sir, you need to turn on your mic. Someone has muted. Sir. Yeah.
Hi, Sammy. Hello.
Sir, would you please unmute your microphone?
okay, yeah. Is it on now? Yeah.
Yes, sir. Yes. Yes.
Yeah. Okay.
Yeah.
So
Okay.
therefore, A2 is bounded by 5 by 2 is the conjecture. What is known for A2 is 20.5. Nothing is known beyond that. And it took so many years to prove, even to bring down to 20.5. How many years? It's about 35 years have gone. Even this conjecture was not proved for n equal to 2 case. It is unfortunate. So therefore, it shows clearly there are not enough tools available to handle problems of this type. So, and hence, you are invited to look at the development on these subjects and see what's missing to solve problems of this type. Okay. Now, what does Cluny-Seal's model did? Look at the harmonic locally univalent map. Suppose I begin with a sense-preserving map, automatically it's locally 1, 1. So therefore, you can begin with a sense-preserving harmonic map, and hence there is a dilatation. I define dilatation omega to be G prime over H prime. So dilatation means W is bound, omega is bounded by 1. So when I say bounded by 1, so therefore omega equals H prime, G prime over H prime, and hence G prime equals omega into H prime. So there is a relationship between the derivatives of G and H prime, G and H, involving the dilatation. That's one thing. Now look at this H minus G, call it as phi. So if you take the derivative of this one, H prime minus G prime equal to phi prime. So if phi is given, omega is given, then you have a pair of two differential equation. One is involving H prime, G prime, omega. Other one is involving H prime, G prime, phi prime. So this is solvable. So given omega, which is bounded by 1, there's a large number of functions that comes from Schwarz's lemma. That's omega, analytic function bounded by 1. That means G prime minus R G prime equals to H prime times omega. You fix omega any damn guy which is bounded by 1 in the unit disk. Say simplest one, is it the omega equal to Z or minus Z squared, minus Z squared, Z power n, whatever it is. Phi could be a function which is a univalent mapping of a domain which is onto a domain which is convex along horizontal direction. What do you mean by convex along horizontal direction? Which is something like every line parallel to real axis, every line parallel to real axis has connected intersection with the domain. If it goes outside, it's empty. So this domain is what is called convex along horizontal direction. But this is not convex along horizontal direction, but it's convex along vertical direction. Okay, so now I call CHT, that's enough for the discussion. So now look at this function, phi. Phi is a Kobe function. If you look at its image, it is easy to see that image is the whole complex plane minus a line from minus 1/4 to point at infinity along the negative real axis. That means remove the half line from negative real axis up to minus 1/4 from the whole complex plane. That's what your range. The range of phi is C minus the interval, half interval minus infinity, comma 1/4. That's half line is removed from the whole complex plane. So when you draw a line parallel to x-axis, of course, it's a convex along horizontal direction. So if you take omega to be identity function, that means G prime equals G times H prime. And if you check phi to be this Kobe function, then that means H minus G is this phi. Now take the derivative of this, and then you have two partial differential equations. Solve for H prime and G prime, and then integrate. You get H and G, and then you call K to be H plus G bar. That is what your harmonic analog of Kobe function. If we determine its coefficients, that's exactly the capital AN, and the coefficients Bn exactly the Taylor coefficients of G, which comes from solving these two. So that sets the problem in the sense of determining extremal function. And this idea helps to say this is perhaps the extremal function for the class of all univalent harmonic mapping of the unit disk. So the coefficient conjecture, the equality holds for these functions where H and G, capital H and G are given by this. Okay, well, what was known before? So before I conclude, what was known before I should spell out. Clunian Silsmal himself proved in the same paper in the same year 1984 when they began the discussion on this topic. They proved A2 is 12,172 as a crude estimate, but the conjecture is pi/2. And it took another 6 years to develop what is called a linear invariant family of univalent harmonic mappings, through which they proved A2 is 57, bounded by 57. And then it took another 14 years to use ideas from quasi-conformal mapping, and then using complete elliptic integrals of the first and second kind through the quasi-conformal theory, and then they brought down this number to 49. But it took another 14 years to brought down to 20.5. And this is the real development whole this year. But on the other hand, this conjecture remains true if we take F's univalent mapping of disk onto a star-like domain. That means the class of all univalent harmonic mapping that are star-like, for which this conjecture has been proved, and the extremal function turned out to be exactly the harmonic Kobe function. So that's the first hint that this must perhaps be true. Second one, look at the univalent harmonic mappings whose range is a closed convex domain. Then also this conjecture is proved to be true where the extremal function is exactly the same. Oh, second hint that this conjecture probably the right. Third hint, if you look at the univalent harmonic mapping whose range is convex along any direction, need not be along real direction. Univalent harmonic mapping taking disk onto a domain which is convex along any direction, that means convex along any direction, then also this conjecture is true where the extremal function in this case also the Kobe function. So these three cases are testing hypothesis to believe that this conjecture would be true, although one was unable to prove this conjecture even for n equal to 2. Once for n equal to 2 is proved, you can prove for, of course, n equal to 3 for Bn also. So B2 is bounded by 1 by 2. That comes from Schwarz lemma. That's only for B2 case, but not for other Bn's. Okay. So therefore, it is a challenging question which requires ideas from other fields. In fact, I use partially some ideas from Jacobi elliptic function to derive this A2 bounded above by 20.5. At one stage, I brought down to 16.5, but the referee has some doubt on the method I developed. So unfortunately, I was not that good on manifolds. So therefore, I am still looking at that problem to take it through some ideas from some Riemann surfaces on manifolds. So therefore, the 16.5 which I have in mind requires to fill some gaps. These gaps seems to come from ideas from Riemann surfaces and some manifold theories, so which is not familiar. Unfortunately, during my college days or even PhD days or later days, I did not really learn seriously these manifolds in the setting of plane setting for Riemann surfaces. So that lacks me to handle this problem as of now. So that's a thing I want to say now. Feel free if you have any questions, and I will be happy to answer. If I know, I say yes. If I do not know, I will answer you later. Thank you so much for your attention. So it's time for questions.
So,
yeah.
So any questions from the participants?
Oh, so as I can see, I mean, there are lots of questions. There are not many questions, but yeah, one question that has been written here at the beginning was about sin z. How sin z is over the complex plane at one of your slides at the beginning.
Yes,
So,
sin that takes whole complex plane into whole complex plane.
yeah,
Is it
that was one question that was written in that box. Yeah.
You mean how sine of C is C, right?
Is it the question or the speaker can, I mean, the person who asked the question can turn on his mic and ask?
Sir, I have a question.
Yeah, please.
Sir, you mentioned Picard's little theorem for meromorphic function.
Yes.
That every meromorphic function phi in the complex plane that omits three distinct values a, b,
Yes.
c is necessarily constant.
Yes.
So, sir, that means if say one value is repeated twice, means it omits a and say b.
Yes.
Then
No, A is taken as one value.
So my question is,
three distinct.
Okay, three means A, B, C have to be distinct.
Yeah, three distinct. Yeah.
So if that means if it is repeated, then it may not be constant.
Yeah, no.
Okay, thank you, sir.
Yeah. I think somebody asked, he said, how sine of whole complex plane is the whole complex plane. So this is simply given a complex number W, you solve for sine z equal to W. Okay, so therefore sine z equal to W has infinitely many values. How you do it? So given W, when W equals 0, there is nothing. You can sine z equals 0, you have infinitely many z's. Okay, because even in the real case it is true. Okay, so if W is a non-zero complex number, then sine z equal to W you have to solve. How do you solve? One way of solving this one is use the definition of sine z in terms of exponential function. Then it can be written as e power iz minus e power minus iz divided by 2i equal to W. Now multiply by 2i on both sides and then multiply again by e power iz. You get a quadratic equation in the variable e power iw. So you get a quadratic equation in the variable e power iw. So e power iw has two solutions. And you will see that these two solutions are non-zero. And then you can solve for iz now. So you get infinitely many values. They come in terms of logarithm. So logarithm of a non-zero complex number has infinitely many values. And you will see that sine z equal to W for a given W, whether W is 0 or non-zero, there is infinitely many values for z sine z equal to W. And hence, each point in the W plane, there is infinitely many values in the z plane such that sine z equal to W. So therefore, sine takes values, every complex value.
Sir, I had a question.
Yeah.
Sir, in the Riemann mapping theorem, we saw that every proper simply connected set is conformally equivalent to the unit disk.
Yeah.
Can we say a similar thing about the whole complex plane? That is, I mean to say that is the whole complex plane?
There is a point. No. We have to whole complex plane. There is a point at infinity, the only boundary point. You have to take two boundary points. So it takes one more.
No, sir. I was asking whether the whole complex plane is conformally equivalent to the unit disk.
No, it's not. It is not.
Okay. Thank you.
This is because of the Riemann. Liouville's theorem says that. So if it is a holomorphic function on C,
Okay.
if you say there is a holomorphic function from C onto the unit disk, that means what?
Okay.
It's an entire function bounded by 1.
Yeah.
So it cannot be none other constant. So constant function cannot be 1.
Okay, sir. I understood. Thank you.
Yeah,
so much.
there is no biholomorphic mapping of disk onto whole complex plane also.
Yeah, sir. Thank you.
Yeah.
Sir, I have one more question.
Yeah, please.
Sir, like you showed that sine z takes every value.
Yes.
And not only that, it takes every value infinitely often.
Yes.
So, sir, if we are given some entire function which is not a polynomial,
Yes.
then that also takes every except one value. It takes every other value infinitely often.
Yes, because see, if you have an entire function, sometimes you get an entire function in explicit form.
Right, sir.
Sometimes you cannot get an entire function in explicit form, but this could be determined by the radius of convergence using this the Taylor coefficients. then it is a kind of infinity, that is an entire function. This also holds for such functions.
Okay, sir. Thank
So
you.
entire function is, it doesn't matter whether you have an explicit form or it is represented by a power series.
Right, sir.
Yeah. For example, there are many entire functions, solutions of differential equations, for example.
Yes, sir.
Yeah. Bessel functions and other things. So you explicitly, some cases you can find explicitly. Of course, in most cases in Bessel function, you have an explicit form in terms of zeros, and then genus and other things. You have to use all that thing. But in principle, every entire function can be written as explicitly using Hadamard factorization theorem in some form through their infinite product if they have infinitely many zeros, whose limit point is, of course, not in a finite complex plane. Limit point must be infinity. Yeah. So you have an explicit form in Weierstrass product representation or Hadamard factorization theorem. So that also holds for this. Yeah. It's for any entire function. Yes.
Thank you, sir. Thank you.
Sir, I have a question.
Yeah.
Like Norshire theorem that you took the convex domain and it implies simply connected. So
Yes.
you were doing that independence of this integral.
Yeah.
So my question is, can we replace some convex domain? Means why this means you are taking this because
Okay.
anyhow we are interested in simply connected. So I am having this doubt. What other domains like we can do for such kind of things like this
Domain,
is the basic.
see, domain other than convex domain, this is not true.
Yeah.
So there are explicit example. If the domain is not convex, then one can construct an analytic function satisfying this condition where f is infinitely valent. There are concrete examples towards that. That's one thing. Second thing, if the zero is
Okay,
replaced
so basically
by,
my concern.
convex domain is necessary condition.
Okay.
It is some sense in the
So
case of real
basically,
variable. In the case of real variable, derivative is positive in the interval. So here somehow the interval is replaced by a convex domain in the complex setting.
Okay.
In the interval is replaced by a convex domain.
Thank
The second important observation is that the real part of this derivative is positive if the zero is replaced by a negative real number, however small it is.
Yes.
Then also this conclusion is not true.
Okay.
So univalency is not there. If zero is replaced by a negative real number on the convex domain, then also I can create an example of a function which is convex, which is analytic, whose derivative is not really bigger than zero, but bigger than some negative number. Then f could be infinitely valent, not only multivalent, it could be infinitely valent. That means...
so I have one more. Hello?
Yeah, please go ahead. Yeah.
Okay. Might be this question may not be like good thing. Like if you said no for all z belongs to D, this has to be strictly positive.
Yeah.
So what if it is like for every z, is it implying that the greatest lower bound of these all positive or it may be zero? Means will it make some problem or not?
No. See, on the boundary it could be zero. That doesn't matter.
Oh, no, not on the boundary. I'm saying if I take the lower bound of all these, means for particular, say for Z1, it is like 1, and for Z2 in the D, it is like 1/2, and the greatest lower bound of these goes to like it is 0.
No, if there is an interior point for which there's a real part of the derivative is 0, then I can prove that it is not just 0 at one point in some neighborhood of that point.
Yes.
So therefore, it cannot be true. If you prove that it is 0 at one point, at the interior point, then I can prove there is a neighborhood of that point where it is actually 0.
Yes.
Yeah.
Yes.
So therefore, it cannot be replaced by that. Yeah.
Okay.
And this is the simple criteria, but the natural question is, what are the other possible replacement for the real part of the derivative positive? Of course, there are many. There are many.
Oh.
There are many conditions which ensues by replacing this by something else. But if you want to do this one, the convexity is essential, and then 0 is also cannot be replaced by smaller number.
Okay. And this inequality, like you said, for real numbers, we take no univalency is like if the derivative is positive and monotone, so f is 1, 1.
Yeah.
So this condition is like is a means it's the motivation for this conditions follows from there, as you said.
Yeah.
So what basically means you said, so there are other conditions. So whether they have also motivation from the real, or is there anything from which we can think like these kind of inequalities?
These kind of conditions are motivated by different factors. For example,
Okay.
If you look at the basic complex analysis in an advanced course, when a function is univalent, what are the transformation which helps to create more examples of univalent function? For example, if f is univalent, of course you conveniently normalized it, then rotation also will lead to a univalent function. Then there is something called dilation. That means z is replaced by z into r. R is any number between 0 and 1. Then this also univalent. Okay. Then you are looking at, suppose you allow f composed with a disk automorphism.
Okay.
So see, there is a complete characterization of automorphism of the unit disk. They are simply Mobius transformation. So there is a class of Mobius transformation which takes disk onto disk. Of course, some conditional ABCD is given. So therefore, f composed such a function is also univalent. Okay, then you normalize it. Then you end up with something like A2 bounded by 2. And if you use that theorem, you get a new condition. Why I want to say that one? The necessary condition helps to create a new sufficient condition for univalency. What is the sufficient condition? For example, by doing that way, you could replace this by, for example, 1 minus modulus z squared. 1 minus modulus z squared times absolute value of f double prime by f prime. If this is bounded by 1, then also f is univalent. So these functionals could be replaced something involving derivatives. Because why derivative is important? Because the derivative is required for local univalency first. So therefore, any formal sufficient condition will definitely involve derivatives. Okay. So therefore, the second derivative divided by the first derivative, look at its absolute value, then factor it out by 1 minus mod z square. If this quantity is bounded by 1, then f is 1, 1. Okay, this is not just to determine a condition. It is just to determine its implication, other fields. This is called the pre-Schwarzschild derivatives. That's used in Theis-Miller's theory. Okay?
Oh, okay.
So that the connection goes, when you compose with a disk automorphism, actually the Schwarzschild lemma has to be in mind. So that led to something else, nice geometric intuition. And that goes all the way from different angle. So these conditions are just, initially it might start from some simple observation. But when you go on doing this in some means, which comes naturally for other means of using, some sort of transformation, elementary transformation sometimes, or omitted value transformation sometimes. Because number of ways one can determine univalent function. Given a univalent function, how can you determine more? How can you determine another one? How can you determine a class of univalent functions? So when you look through those kind of ideas, one should look at a kind of geometric intuition to replace this one, leading to the univalency. Yeah.
Thank you, sir.
Any other questions? Sir, I have a question.
Yeah, please.
that does there exist any classification for non-essential singularities?
See, the classification of singularities are divided into two categories.
Sorry, non-isolated singularities. Sorry. Yeah.
Non-isolated essential, I do not see any classification of that.
Yeah.
At least as per my knowledge, there is not much classification of that.
Actually, there is just a term in your book that just essential non-isolated singularity like that. Actually,
There may be other use of non-isolated essential singularity, no doubt, but I do not know the classification of non-isolated singularities. In a relatively general term like pole, singular, pole, essential, removable, not in that kind of names, at least. There must be inbuilt classification while proving a theorem related to that.
Okay. Yeah.
But the one interesting thing is that the Picard's great theorem or Picard's little theorem, it uses an idea of Landau. Landau's theorem says that if you have a non-constant analytic function defined on the unit disk, the range contains a disk of some positive radius.
Okay.
Of course, you use a normalization in order to conveniently ask this question. Look at a normalized, normalized in the sense that derivative of the origin is 1, for example. Okay. So that shows that the function is non-constant. So if your derivative of the origin is 1, look at the univalent, not univalent, just an analytic function defined on the unit disk. Then the Landau's theorem says that the range contains a disk of some radius. Okay. Given f, I can find, for example. Okay. So then I have to look for all f. You have to look for all f. So you want to look at the the smallest of all numbers. Okay. Yeah. Okay. So that number is actually a universal constant. That means there is a universal constant independent of f. But there is a conjecture about the lower bound and upper bound. And that problem is still unsolved. And the existence of universal constant for which there is a disk of positive radius in the range is the one which gives you a proof for the Picard's little theorem. So if you look at the Picard's little theorem and Picard's big theorem, you will see this Landau's theorem plays a role. It is not just analysis that they use; it uses in some other way always. Although the conjecture remains open, but it's good enough to handle for many problems with such kind of conjectures or some lower bound or upper bound on that.
Yeah.
So there is one more question in the chat box.
Yeah, please. Is it?
Is there a harmonic analog of gamma function?
Harmonic analog of gamma function. I did not see as of now whether somebody has done it or not. I mean, how naturally it comes, it's very important. Yeah. Not like putting gamma of z and then plus gamma z bar. It's not like that,
Okay. So I have a question.
Yeah, please.
Yeah. Go ahead. So in real line, there are many functions. In real line,
yes,
there are many functions which are infinitely times differentiable, but its Taylor series expansion actually not converging to that function. So what is the reason behind this?
See, analytic functions are always infinitely differentiable. Remember that.
Yeah. I am not talking of complex plane. I am in R.
Okay, you are in R.
Many differentiable functions, but its Taylor series expansion is not converging to that function. So what is the reason behind this?
No, see, it is related to, I think when you look at a uniqueness theorem, you will see if there are examples of function.
So, or explicitly, my question is,
voice is breaking.
Because
Is essential singularity playing some role here?
Because the power series leads to that problem, you know.
Okay, suppose e to the power minus x square by 2.
I remember that e power minus 1 over x squared. Yeah.
So is essential singularity playing some role here?
Because there is, it means it's not the essential singularity. The essential singularity business comes to only the complex variable. See, the power series which represents that function holds only at origin. That's what the thing. Yeah.
Okay.
The function is infinitely differentiable, you know. The function is infinitely differentiable, but when you compute the power series representation, you know, for some interval it is 0, for some other interval it is explicitly you determine that function. I think I remember that example in real variable. Yeah.
Yes.
Because all derivatives at the origin is 0. So when you look at the power series form, the power series leads to 0. I mean, that means that represents only at the origin. Yeah.
Okay.
Yeah. Any other questions? Yeah.
Okay. So I think somebody is asking you to explain something, but I don't know whether we have time or not. So he is asking, explain isogonal mapping to conformal mapping, if possible. Is isogonal mapping to conformal mapping possible?
See, for example, is a sense preserving, sense reversing, for example.
Yes.
You know. See, if you look at Z and Z bar, Z and Z bar, okay, both are univalent. So here the angle is preserved, but not in a sense and magnitude. You know, it's a conformal mapping. When I say angle preserving map, it is preserved both angle and in the sense of see what I mean is, for example, look at Z and Z bar. Okay, so when you compute two lines, for example, look at the real axis, look at the function in Z and Z bar for conveniently. For example, the simplest example, look at the identity function. Okay, look at one curve as a real line, other curve as the complex positive real axis, imaginary axis. So these are two curves. The angle between them is pi by 2. It's right. Look at the image curve. The image curve is image of real axis under the identity function is the real axis. Image of imaginary axis under identity function, imaginary axis. So angle between them is pi by 2. And if you look at Z bar, if you look at Z bar, then the image of the imaginary axis is the negative imaginary axis. Positive to imaginary. So the angle between them is pi by 2, but not in absolute value. It is in absolute value, but not in, you know, by covering, when you want to measure the angle from 0 to pi by 2, here you get minus pi by 2, 0, it's minus pi by 2. So it's not angle preserving, it's angle preserving is theta is minus theta. So therefore, that's the way isogonal mappings are defined. Yeah.
So I have one question more. So may we have some general complex integration theory over some division ring?
I do not know. I have not seen such things. Of course, the several variable point of view, there are many things, but other aspects I do not know.
So actually, if I drop the commutativity,
yeah.
So then it is one of interesting question of mine that can we generalize the complex integration theory over some division ring?
Because there are, I guess there are similar such attempts like bicomplex numbers, and all that things are also there. But more in general, before one introduces, people used to think, is there some way to link with some applications are there when people used to think about it? Yeah, certainly. So initially you want to set in a different setting, but one has to look at whether by doing so, are you going to gain something in terms of application or connecting with some other field. So only then one can look at it carefully and then see how the structure of complex numbers, the basic complex numbers, work towards that goal, and then where you can define derivatives, all that thing. Then one could perhaps think on that line. Yeah.
And can you bring the same flavor of integration theory in the rings of complex valued function?
Possibly, but one has to look at it. Yeah, it could be. Yeah. Once the basic ideas are developed, possibly one can think of that. Yeah.
Okay. Possibly,
I cannot imagine for the moment, but one has to look at how one can define, the Riemann sum and all that thing in that setting. Yeah. So, yeah, once that is done, of course, yeah. So integration theory, we do, what is the analog of that one? Like in the case of graph theory, people develop, discrete graphs, discrete Hardy space, So they use the same setting, but you have to carefully, allocate the one-to-one correspond between these two aspects. Yeah. Then one could define various means, maybe. Yeah.
Thank you.
Yeah.
Okay, so I think there are more questions, but we have to stop somewhere.
Yeah, they can write to me, no problem. Yeah.
Yeah.
Yes.
Yeah. So one thing I would like to ask you. So I see there is a huge demand for video recording of your lectures and PowerPoints. So if you don't mind, can we post it on the YouTube so that anyone can access?
If you think it's useful, you can put it, no problem.
Okay. So then, Abhishek, I think it's better you post it on the YouTube, because
but
okay.
you try to edit it. Maybe you can edit it.
Before posting, I will send it to sir, and if he permits, then yeah. Okay.
Yeah,
if everything comes okay, and if some interruption can be edited, that's fine, no problem. Yeah.
Yes.
Yeah, no, he will send it to you for approval before posting.
No. If you think it's good, useful, you can always,
No, it will be useful. I mean, it's a fantastic lecture. Thank you very much.
Yeah.
So
this is just prepared in a couple of days quickly. So
yeah, I know that. Yeah. So thank you very much, Professor Ponnusamy.
Thank you so much for giving the chance to talk to you all, and it was nice experience.
No, I thank you because
no problem.
In spite of several hectic schedule.
No problem.
Business, you managed to come here. Yeah.
No problem. It's welcome. It was nice experience for me also. I spent only yesterday one full day. It is good. I mean, at least for some, as long as it's useful to some others, it's very good.
Yeah. So I hope that you will join us again physically at some point, and we can have more of your lectures in terms of course or something like that.
Initially, I was planning to develop only on Picard's little theorem and Picard's great theorem.
Yeah.
But some of because the title was invitation, so I need to push some agenda. so therefore, I changed a bit with some background of known things with new ideas.
No, it was very interesting.
Okay.
It was very interesting.
Yes.
So thank you very much.
Okay, thanks a lot. Bye.
Yeah.
Good. Yeah. Thank you.
So we will post it on the YouTube for the participants. So that because there are around many participants, and it's not possible to email everyone perhaps.
Okay.
So we will just post it on the YouTube, and whoever wants, they can have a look at it.
Okay.